Howdy folks, this is our pre-work for section 17.3, which introduces the idea of conservative vector fields. So first I've listed our goals for this section. We'll start off with some terminology that we'll need through the rest of this unit. We'll introduce the idea of what it means to be a closed curve, a simple curve. We'll talk about connected and simply connected regions, and all of those are building up for the definition of what we want to call a conservative vector field. So then we'll learn how to classify whether or not a given vector field is a conservative vector field. Then what we'll learn how to do is to determine the potential function which generates a given conservative vector field. And all of this is building up for the fundamental theorem of line integrals, which gives us a really nice way to evaluate certain line integrals with certain types of vector fields. And that's what we're building towards, and then once we're done with that, we'll look at some of the properties. So these are our goals for this section, and in the pre-work we will cover the first three of these, and we'll leave the larger two for in-class work. So let's go ahead and get started. We're going to need some terminology in order to define a conservative vector field. So the first thing we want to do is we want to define what it means for a curve to be simple. So let's just start off supposing we've got a curve situated in Rn, and we've got some sort of parametric description of that curve on some time values ranging between t equals a and t equals b. So this is the type of curve we've been working with, and we want to say that that curve is a simple curve if what? Well, it's going to be simple if r of some time value a, we can't use a here, r of time 1 does not equal r of time 2 for some t values t1 and t2 on the interval. One thing to note is I'm not including the endpoints here. Notice this is a strictly less than symbol here and a strictly less than symbol here, so we're not including those endpoints. We'll look at the consequences of that in just a second. The other thing we want to define is what it means for a curve to be closed, and a curve is said to be closed if r of a is equal to r of b. So those are our two new definitions, what it means to be a simple curve, what it means to be a closed curve. In layman's terms, what we mean when we say a curve is simple is that it never intersects itself, except for possibly at the endpoints. So it doesn't have to intersect at the endpoints to be simple, but if it is simple, it can never intersect itself on the interior, and that's why we use the strictly less than symbol in our statement of the definition. And what does it mean for a curve to be closed? Well, it's closed if its initial and terminal points are the same. So one way to look at that is that this curve starts where it left off if it's going to be a closed curve. So let's go ahead, and what I'd like you to try to do is pause the video and try to sketch curves that satisfy each of these criteria. The first one being that the curve is closed and simple, and you'll run through the various other permutations of that, and we'll take a look. So pause the video, fill this part in, and then we'll resume. So folks, what I did here was I went ahead and sketched curves satisfying each of these requirements. You'll notice in the first example we've got a closed curve. How do we see that? We see that in that r of a is equal to r of b, meaning we end up where we finish. And this curve is simple because it never intersects itself, except for, in this case, at the endpoints. But remember, we allow that to be the case if we're considering a simple curve. In the second example here, we certainly have C as a simple curve. It never intersects itself, and it is not closed because the two endpoints disagree with each other. By the way, all of these I'm sketching as if they're in R2. Sketching curves in R3, it's very hard to tell whether or not they actually intersect themselves. So these are all in R2. For the third example, we want a curve that is closed but not simple. So again, you can see that the two endpoints agree with each other. But in this case, because of this point right here, so we have, some r of t1 would equal r of t2 for two different t values. And so this would be not simple because of that intersection point right there. At two different time values, it passes through the same point in R2, so then it can't be simple. And then finally, we have an example of a curve that is that is not closed because the two endpoints disagree with each other, and it's not simple because, again, we have this point here which presumably exists for two different time values. By the way, on all of these I gave orientation arrows. You didn't need to give orientation arrows, but I found that was helpful just for talking about the starting point versus the ending point. So that's the only reason why I included orientation arrows on that. So now that we've given some definitions for curves, we want to give some definitions for regions. You can think of these as surfaces or regions sitting inside of some sort of either 2- or 3-dimensional space. And so let's just suppose that D is some open region in Rn. Then we're going to say that D is connected if it is possible to connect any 2 points in D with a continuous curve lying entirely in D. Meaning it's possible to get from one point in D to another point in D without ever having to leave it. So you can draw some sort of continuous curve that stays within the region D as you move from one point to another. The other definition we want to give is what it means to be simply connected. So a region D is simply connected, according to our author, if every closed simple curve in D can be deformed or contracted to a point that is also in D. So what we mean by that is that it's possible to, if you take some curve, let's say we have some region D here, and we take some simple closed curve like we were just describing before. So maybe here's a simple closed curve that's lying entirely in D to begin with. If I were to contract this down, I could make it smaller and smaller, and if I kind of shrank it down, I would arrive at a point sitting inside of the region D, and that's the key, is at that point that you can contract it down to, you could, if you imagine maybe squeezing this curve down into smaller and smaller pieces, kind of deforming it down smaller, it arrives finally at a point P, but that point P is still part of our region D, and that's the key part there. One quick note, folks, is that our author allows for the possibility that a region can be simply connected but not connected, and not all authors agree on that. So if you take some topology classes, you might see some discrepancies with what we've just defined. Okay, so now what we'd like to do is we'd like to go ahead and sketch some regions in, we'll go ahead and do these in R2 again, where we have that D is connected and simply connected for the first one, and then we permute through those other possibilities. So go ahead and again pause the video and finish filling these out, and then we'll check our answers here in just a moment. So pause the video and then resume. So folks, I'm going to go ahead and construct these with you. So the first region needs to be a simply connected region. So this could be a region possibly like this region here. And the first thing I want to say is that according to our definition, this needs to be an open region. So I'm sketching the region in blue. The region is this filled in area in blue, and I went ahead, just so you can see it well, I sketched the boundary of it in green, but the boundary is not considered part of that region. That's a finer point that I'm not going to worry about, but I thought I'd mention that. So this region is certainly connected. Why do I say that? Why is this region connected? Well, if I take this point right here, A, that's in the region, and this point B over here that's in the region, is it possible to construct a continuous curve that will get me from point A to point B, and to ensure that that curve always lies in the region? And sure enough, I just did so. It's also considered simply connected because if I take any loop inside of it, like this loop right here, I could contract that loop down to the point that I've just sketched, and that point lies inside of my region D as well. So now let's go ahead and sketch a region that is connected but not simply connected. So an example of that might be something like this here. And let's go ahead and put a hole in this. And again, folks, this is technically an open it is an open region. I'm sketching the boundary in green just so we can see it well. I tried to sketch it dashed and it didn't look very good. So I sketched the boundary in green, but the boundary is actually not part of the region. This is an open region. Anyway, this is not considered a simply connected region. How come? Well, if I took, say, this loop right here, here's a closed loop sitting inside this region C, I'll label it C1 for that closed loop. If I were to contract that down, it would contract down to a point in the region. But if I were to take this curve right here that I just sketched here, let's label that C2, if I were to try to contract that loop down, that closed curve down to a single point, I couldn't do it, or that is, I would arrive at a point that's not inside the region. And so that means that this region, while it's connected, again, labeling any 2 points in there, you can sketch a continuous path between them. It's not simply connected because of this hole inside of it. Now for this third illustration, we want a region that is not connected and not simply connected. So an example of that might be something like this, where we've got the region D is actually two separate regions put together. So we could even, we could say, maybe we call this D1 and this D2, then we would say that our region D is the union of those two regions. So again, the D is the blue shaded region here, and you can see that it's not connected. How come? Because if I took this point A here in D1 and this point B here in D2, it's impossible for me to sketch a curve that will get me from A to B without leaving the region. There's no continuous curve that will get me from point A to point B. So that's our definition that shows that we don't satisfy the definition of being connected. And then it's not simply connected for the same reason that we had up in this example up here. So the final one then is an example of a region that is simply connected and not connected. So an example of that might be something like this. Again, we'll have two separate blobs, I guess, for our region. Maybe we'll call this, D3 and D4. So here our D is the union of D3 and D4. And so for the same reason we saw before, if I took, if I take, A here and B here, it is possible this subregion is a connected subregion. But if I took some point C over here, it's impossible for me to give a path from point A to point C without leaving my region. And so for that reason, we would say that the D, the union of these two, is not connected. It is simply connected though, because if I take any loop that lies entirely inside of it, any closed loop, then I can contract that down to a point. So hopefully folks, that clarifies these two definitions of what it means to be connected and simply connected. And we see examples of regions that are simply connected and not connected here. So now we want to return to a question that we asked way back at the beginning of this chapter, and that was when we introduced the idea of a gradient field and its potential. So the question we asked is, when can a vector field be expressed as a gradient vector field? As a reminder, what did that mean? That means that that we were able to generate that vector field from what we called a potential function. And we labeled that potential function phi. So we will call such vector fields conservative vector fields. Conservative vector fields. And we want to explore the special properties that line integrals have when we're working inside of a conservative vector field. So let's go ahead and give our definition for a conservative vector field, and that'll finish up this first video. So there's not really a lot new to this definition of what it means to be a conservative vector field. It's related to the potential function and the gradient field that we talked about in section 17.1. And so we'll say that a vector field is said to be conservative on a region if there exists a scalar valued function. So by that I mean, it might be some either phi of xy or some phi of xyz if we're talking about a vector field in R3. And it's going to be conservative if there's such one of those scalar functions so that the vector field is simply equal to the gradient of phi. If that's the case, meaning if we've got a vector field and we can think of it as arising from taking the gradient of some scalar function phi, then we're going to call it conservative. By the way, if you're interested about that phrase conservative, it's related to the idea of conservation of energy. It's a similar notion there. That's where we use the word conservative from, although we won't be diving into that in this lesson. So this completes the first video, and we'll pick up in the next.